right, good evening. Thank you for staying over for the last session. I'm Jacob Zahavi. I'm the CEO of VMware Analytics. This is a kind of a new startup established not long ago and located here in Jerusalem. And I'm going to talk about the objective of VMware is to automate the process of building large-scale predictive analytics model, and that's the kind of topic I'll be speaking about here today. Now, the objective of VMware is to make predictive analytics accessible just about to everybody, so that even the novice business users can build a predictive analytics model at a quality which is at least as good as, if not better, than models built by experts in this field. Not, of course, the cost of building models and the risk of the cost of building models in an automatic manner is much more lower. The risk is smaller, and also this allows to increase the throughput of models and allow to implement models over many applications, and thus bring more value to the organization. Another attribute of our system is the fact that we create a open system. It's not an open. It's an open box system where the curious user can actually track the results and see at each stage of the process what happens, and if necessary, calibrate the parameters and rules to make it more suitable to his or her organization. In terms of agenda, I will say a few words about what is predictive analytics, and then I'll talk a little bit about the problem characteristics and the components of our system. I don't think I'll have time to go into detail on each of these items, but I'll focus more on the more unique features of our system. Predictive analytics, I'm sure you all know it. This is a data mining models where you've got predictors coming in, like in this case, your age, customer, current balance, recent purchase, and you put it through a model and you predict something. For example, will customer buy the product? So based upon past observations, past history, then we're trying to predict the future, and of course the information which takes part in the prediction process is domain related. It varies between domain. The information in marketing is not the same as the information that is used to predict in the finance world, and so on and so forth. Two major problems in predictive analytics, classification and prediction. Again, I won't focus too much on it. Classification is assigning observations, to a small set of predefined classes. The simplest way is a two-way classification to assign an observation to a yes and no class. For example, in marketing, whether you are a buyer or non-buyer, whether you'll churn or not churn to another company, and so on and so forth. And prediction is a similar problem, except that the dependent variable is continuous. We're trying to predict a continuous variable, like money spent on purchasing from a catalog, or money donated to a charity, and things of this nature. And by and large, the leading models for predicting continuous response are regression models. And as you can see from this chart, there are a bunch of regression models: linear, logistic, multinomial, neural network, genetic algorithms, and others. Each type of regression model applies to a certain type of problem or certain type of application. Well, our current focus is based primarily on regression-based methods. So we're going to use linear regression for estimating continuous response, and a binary logistic regression model for classification. And at the moment, we're only focusing now on the binary case, yes or no. Now, what is the problem characteristics? The number of observations may run in the million, and the number of attributes in the thousands, and that's not including transformation and interactions, which I'll say a few words about, which may increase this number even further. The relation with the output variable are not necessarily linear, so we need to take that into account. Plus, there are many other issues that characterizes regression models or large-scale regression models, like highly correlated with other predictors, noisy data, predictors which are irrelevant. There are some rare events. So all these issues need to be concerned when building a very large scale regression model. The challenge, the market currently offers analytic tools like SAS, SPSS, S+, R, and not a solution. So by and large, the user in this environment assembles his or her own solution and determines, the kind of procedures to use and their sequence. Usually the process is done iteratively, where the user, tries a solution and then evaluates it, try another solution, evaluates it, and pick up, the solution that he thinks is the best, even though this may not be the optimal solution. The process is costly and time-consuming. Building predictive analytic models manually may take anywhere between a few days to a few weeks, depending upon the size and the complexity of the problem, which may be too much, for today's dynamic business environment, where one needs to build predictive models at a much faster rate. Sometimes daily or even less than, or even hourly. Response time to build models, I said, it's too long for today's online system and emerging operational intelligence platform. Lack of knowledge and expertise may lead, I would say, to poor models. And on the other hand, the era of the big data actually increases the demand for predictive analytics, which makes the automation issue a much more crucial problem in today's world. Okay, so we meet this approach or this challenge by using an expert system that actually mimics the way that an experienced data scientist goes about building large-scale model. And we took that process and we actually computerized it. So the process is controlled by a set of rules and parameters that were calibrated over the years based upon theory and practice of machine learning and statistics, our extensive experience in building and using PA models, and of course even our intuition. And we've implemented many components of this approach in the previous software, and now we are enhancing this approach and redeveloping to be compatible with the new IT technologies, online systems, web, and allow to implement it in real time. We provide an end-to-end solution that has this component, pre-processing, splitting into training and validation data sets, feature extraction or feature engineering, feature selection, model building, knowledge evaluation and decision-making, model deployment, and model maintenance. As I said, this is too long of a list to be able to cover in a few minutes, so I will focus primarily in this presentation on the feature extraction, feature selection components, which are the most complex and intriguing components of building very large predictive analytics regression models. Okay, pre-processing, we all know this is a mandatory step in preparing the data for modeling. It consists of exploratory data analysis in order to understand the data and check the input data. Of course, fitting in missing value or missing data is really an important component of the model building process, because missing data is a very common phenomena in data sets, especially large data sets. We need to identify extreme value, identify outliers. All of that is done in pre-processing. I'm sure that you are aware of what pre-processing is, so I will just skip and go to the next slide. This is a validation training data set. This is also part of the pre-processing process, where we actually take our analysis audience and split it into two data sets. One called the training data sets, used to build the model, and the other one, the validation data set, in order to validate the predictive analytic modeling results. I should mention here that unlike in conventional regression models, okay, the emphasis in predictive analytics is not so much on building accurate model, on fitting the data very well, but rather on the prediction accuracy. So in order to be able to assess the prediction accuracy, we need to actually build the model on a separate data set than the one used for, and then use a separate data set, the validation data set, to check the prediction accuracy and to see how generalized is the model and how well it can be applied to new observations. All right, so feature extraction, or sometimes call it feature engineering, is actually conducted by means of transformation, and the transformation are used for several processes, for several objectives. One, for expressing nonlinear relationship, which we know exists between the independent variable and the dependent variable. In fact, I would say that by and large, most of the independent variable are nonlinearly related to the dependent variable. So we need to take into account this nonlinear relationship in building predictive analytics model. We want to render prediction more power, and that also can be done by means of transformation and grouping to reduce dimensionality. I'll give you an example of a grouping, like if one of your predictors is occupation. Now there are many occupations, could be like 100 of them, and it doesn't make sense to introduce each one as a separate predictor to the model, because you wouldn't have enough data, enough information to be able to estimate a significant coefficient for each of these predictors. So the idea is to actually group these predictors to collapse them into predictors which have more prediction power. So that's also a type of transformation that we apply. Another type of transformation is interaction, which in order to account for variation of a variable with respect to another variable. To give you an example, we all know that female may be less sensitive to prices than males. Okay, in which case, there's an interaction effect here between gender and price that we need to take into account. If you ignore this interaction, you may get wrong models. Another type of interaction effect is, for example, in a purchase application, in a targeting application, where older females, say, tend to buy a product versus a young male also tending to buy this product. So in that kind, this kind of phenomena could be addressed by introducing interaction effect, which is which is basically given by the product of the two primary effects, say male and gender, or male and price in the example I just gave you. And finally, finally there are domain-related transformation. We know that in many cases, transformation of original variables may have more prediction power than the original variable themselves, in which case, we need to define those domain-related, those transformations which are by and large domain-related. Okay, and here is a list of transformations that we apply automatically in our system, because you don't know, which nonlinear transformation exists between the dependent variable and the independent variable. So we create a bunch of automatic transformation. These are the transformations which gets generated for a numeric variable. As you can see, we can use the raw variable as a predictor, or the so-called overlapping, piecewise linear transformation, binning, chi-square transformation. So these are created automatically for each continuous variable. Now each group of this transformation is we call it a variable representation. Each of these blue bars is a predictor, and the collection of all variable representation for a given variable are close substitute. Why are they called close substitute? Because in the final model, we only need one of these representation in the model. We don't need them all, or none, if that particular variable does not contribute anything to the prediction power of the model. If we're dealing with a categorical variable, there are also some automatic transformation which are specific to categorical information variables which get generated automatically by the system. I will skip, some of this transformation and switch directly to the feature selection system. Yeah, question? Yeah, we calculate it, yeah.
Try some stuff and see what works best.
No, we actually create for each, let's say for each continuous variable, we create all these predictors, all this transformation. For categorical variable, we create all this transformation automatically. Interaction, we also create automatically by multiplying, by the product of two main effects. And then, indeed, after creating all this information, if you combine it with the original set of predictors, you get a very, very large set of predictors or potential predictors to select the final predictors for the model. And this is the feature selection process, which by and large is the most complicated stage or aspect of building large-scale predictive analytic model. Okay, it is very, okay, I will skip this because I don't have much time. And let's jump right away to our approach for feature selection, which, as I said, uses an expert system methodology. It is a multi-step process, where in each step of the process, the engine calculates a host of statistical measures which are relevant to that particular step. And then we apply a set of rules or parameters which uses these statistical measures in each step in order to determine what is the status of each predictor in the model, whether to eliminate it up front or whether to retain it for the next stage. And the process continues in this way until all termination criteria are met. So it is a multi-stage problem, and this is what we do in each of these steps. Let me try to cover them quickly. So the first one is a univariate analysis. What we do here, we actually look on each predictor individually, and based upon the unidimensional statistical measures, we eliminate the so-called noisy predictors, highly correlated predictors, predictors with high p-value, predictors causing perfect multicollinearity, and any other troublesome predictors that we can think of, which may vary sometime between domain. The next one is done at the variable representation analysis. This is basically a correlation analysis for any representation of a variable, and we simply eliminate if there are two highly correlated variables within a variable representation, we eliminate one of them. Which one we eliminate? We eliminate the one that has a lower correlation with the dependent variable. So we basically are eliminating the weaker variable. Okay, next step is the intra-variable analysis. Okay, and as you may recall, there are for each variable we've defined several transformations. We now have to pick among these several transformations the one which is the best for that particular variable. So we use a regression analysis here in order to figure out which of the variable representation is more representative of the variable. Okay? And next step is the intervariable analysis. So after getting to this step, we are left with only one representation for each original predictor. And now the next step is to decide, which of these variable representation to consider for the final model. There are a bunch of methods one can use in order to do that. Stepwise regression is the leading one. Genetic algorithms, simulating annealing, variable reduction methods like PCA or other methods. And this is by far the most complicated step in our feature selection process. But after this process is done, we are basically left with the final set of predictors that are candidates to go into the final model. There is another step here in which we fine-tune this list further by estimating the model, checking the statistical properties of the predictors, and if we still find predictors which are weak, have high p-value or close to zero coefficients and so on, we eliminate them and we re-estimate the model over and over again until all termination criteria are met. So as you can see, we do this process. This is a step. We do this process in steps, and we're going from one step to another. In each step, we actually filter out irrelevant predictors, and until we get to the final set of predictors. The process is very flexible. We've applied it on problems which have hundreds of predictors, potential predictors, and we are still trying to improve the convergence, the scalability, in order to make this process much faster. Okay, so basically I have some output here which I don't have time to cover. Model deployment, model maintenance, so let me just summarize. Okay, so there's a new, I think we have created a new market segment, expert system for predictive analytics, which is fully automatic model, it is a fully automatic model building process based on proven expert system technology. It is generic rather than ad hoc solution. It reduces the time, cost, and risk of building predictive analytic models. By and large, yields better models than human experts, and we have experimented with this approach on hundreds, and I'm not exaggerating, on applications to make sure that we're creating good results. And the end result is that the goal, the objective is to make predictive analytics accessible to everyone and operationalize analytics through the enterprise. Okay, better prediction translates to more efficiency and higher ROI, and the potential of predictive analytics nowadays is very large because of the era of big demand, which creates more and more demand for building models in order to entertain many, many business applications. Sorry for rushing, but that's late, but thank you. Incidentally, I didn't mention it, but you guys can go to our website, www.dmway.com. You have an option there to download our system and experiment with it on your own data or on data that we provide in the site. We check correlated later on to actually.
So then you generate them and then you remove them?
No, we don't. There are some transformation where we don't have to check correlation because we know that by the way they were created, there's no correlation between the predictors there. But there are some correlation where we know that there are some transformation where we know that correlation may exist and we check them. We don't do back and forth. So we only check transformation for which there could be some correlation in order to eliminate one of them.
So thanks again, Professor Zavi.